We've reached the end of this journey where we've laid the groundwork for a simple and structured approach to material selection in design. We've also tackled two of the most common cases in mechanical design: projects driven by stiffness and those driven by strength. In all these cases, we've tackled the problem with a common approach, starting with a conceptual step where we translated the project requirements, outlining them as functions, constraints, objectives, and free variables. Next, based on this translation, we first filtered out unsuitable materials and then classified the remaining ones according to their performance, before carrying out a feasibility study on the possibility of using these materials in the final documentation phase. The examples we've worked through have helped us understand how to approach this type of project. However, there are many other project areas where the same approach can be adapted and applied, but we won't be able to explore them all due to time constraints. That's why, in this final lesson, we wanted to offer other scenarios where the material selection method can be applied, so as to highlight its potential and provide inspiration for anyone interested in further exploring this field. We've seen that the key point of this approach is being able to define and quantify a material's performance using performance indexes. Sometimes these can be very simple and correspond directly to a single property of the material, like stiffness, while other times they combine several properties, as in the case of specific stiffness or specific strength. However, materials have many other properties and many requirements to meet. Even just staying within the field of mechanical design, other indexes can come into play. For example, when you want to design to optimize fracture resistance, or resistance to impact or shocks, or finally, when you want to optimize resistance to abrasion and wear. So, in problems related to thermal conductivity, we won't just limit ourselves to choosing the best conductors or the best insulators. Some indexes will combine different properties. For example, in the case of resistance to thermal distortion, you choose materials with high thermal conductivity and a low coefficient of expansion, while in the case of designing heat exchangers, you look for materials that optimize both conductivity and strength, so you can make thinner and more efficient tubes. The same thing happens in cases of electrical conductivity. In some cases, we simply want to optimize the material's ability to conduct, as is the case with underground cables. But when the cables are suspended and therefore need to be able to support their own weight, conductivity must be combined with good mechanical properties. Finally, when the requirements concern aesthetic aspects, that is, sensory or expressive qualities, we enter another field of design. Here, the goal is to convey sensations. For example, from a functional point of view, a bottle is always a container, but if it's made of metal, it will appear rigid and cold. If it's plastic, it will seem light and flexible, and if it's glass, it will look transparent and bright. The same object, depending on the type of material, can convey different sensations. In any case, some sensory aspects of objects can be linked to the properties of the materials, and there are indicators that can describe this type of performance as well. For example, the sensation of softness or hardness to the touch can be described using a material index that combines stiffness and hardness. In the same way, the fact that a material feels hot or cold to the touch depends on certain properties, and as indicated in the indexes, specifically on thermal conductivity, specific heat, and density. Finally, the sound produced by a material depends on a combination of stiffness and density, which determine its tone, and also on the material's ability to dissipate energy, which will make it sound either brighter or duller. Another area of design concerns environmental sustainability, a factor that's becoming increasingly central in engineering and design. The environmental impact of a material can be described by its embodied energy, meaning the energy required to produce or extract 1 kilogram of the material, and by its carbon footprint, that is, the carbon dioxide emitted during this process. These will be the parameters to minimize in the design process if we want to reduce environmental impact. And clearly, introducing a new objective also means introducing new indexes, which we see represented here in the case of a tie rod, where we want to optimize various aspects, including environmental impact. You can also notice how the indexes aimed at minimizing environmental impact have a very similar formalism to those used for minimizing mass or costs. The formulation of these new performance indexes is therefore relatively straightforward. However, it is not always easy to find information related to the embodied energy of the material or its CO2 footprint. Moreover, accurate design should take into account the entire life cycle of the product, from its production phases to its final disposal. This means making the design process more complex, but even in this case, there are material selection strategies that actually integrate with this type of design. Another aspect of material selection concerns the combined choice of materials and shapes. In fact, to improve the mechanical efficiency of a product, you don't always have to rely solely on the material. In some cases, choosing certain geometries can make it more advantageous to use specific materials. Basically, it's about distributing the material efficiently within the section of the part. A simple example is tubular sections, which make the component stiffer and stronger while using less material. Another approach is to modify its microstructure, as in cellular materials or foams, where the solid material is replaced by a network of cells and voids. These new particular arrangements of material can be described using specific parameters, the shape factor, phi, and the microstructural shape factor, psi. In advanced design, these factors can be incorporated into performance indexes to find more efficient solutions that combine material and geometry, thus creating new rankings of materials best suited for a given application. One last important aspect in advanced material selection is dealing with more complex problems. Sometimes more than one constraint affects the design, even when aiming for a common goal, like when we want a product that is both stiff and strong, but also as light as possible. Other times, there is only one main constraint, but several objectives to meet, which may even conflict with each other. For example, when we want a product that is stiff and also minimizes both mass and cost. In this case, it's necessary to consider multiple performance indices, which are useful for comparing and evaluating the various solutions. Having more performance indices means getting more rankings. But if the same materials don't always appear at the top of each ranking, which one among them can we really consider the best? To handle these situations, practical strategies are needed, and there are several paths that can be taken. For example, we can remove some constraints that influence the project or make certain objectives less strict by downgrading them to constraints. Then, with more advanced techniques, it's possible to keep all the indices active and find compromise solutions, resulting in more objective answers and identifying the most suitable material for different design scenarios. In all these cases, it's important to refer to additional resources that help consolidate and guide the approach learned through this course. Among Professor Ashby's books, we recommend these 3 titles. The first one is for those who want to focus mainly on the material selection method. The second one is for those interested in aspects related to materials. And the third one is for those focused on eco-sustainability. Finally, for those who have the opportunity, we recommend using the Granta software, both for the chance to practically apply the approach developed here to a wide range of materials, and for the learning section of the software, which contains a rich selection of documents and case studies to help you improve and deepen what you've learned in this course. With this overview of other possible design scenarios, our course on optimized material selection comes to an end. We've learned that choosing a material doesn't just mean looking for the strongest or lightest one, but it's about knowing how to interpret the needs of the project, describing and quantifying them using appropriate parameters, and meet them through the properties of materials. We've seen how a structured approach, based on performance indexes, allows us to compare different materials and find the best solutions, the most effective and consistent one with the project's goals. This course have also shown to those who want to continue along the path of material selection how advanced aspects such as shape, microstructure, sensory or environmental factors, and the presence of multiple constraints and objectives can be incorporated into the workflow as true design tools. Choosing the right material is not just a technical matter, it's a creative and strategic process, a bridge between science and imagination. It's about being able to use scientific knowledge and turn it into design solutions that combine functionality, aesthetics, and innovation.